It's a NEET 2016 question basing on laws of motion and of course conservation of momentum and change in momentum is also playing a different important role here. The problem is like this. A rigid ball of mass m strikes a rigid wall at an angle 60 degree and get reflected without any loss of speed as shown in the diagram. What's the value of the impulse imparted to the ball in this journey, right? So the first thing that we need to know, what do you mean by impulse? When a body moving hits some another surface, a large force acts on a body for a short interval of a time, that is called impulse. Force can be written like ma delta t. Acceleration can be written like change in velocity by rate of change in velocity. So these dt's will cancel. So impulse is nothing but m into delta v, that's nothing but mass into change in velocity, that's nothing but change in momentum. Yeah, change in velocity is m v final minus m v initial, that is mv final mv initial, that is final momentum minus initial momentum, that's nothing but change in momentum. So when someone asks you to find impulse and force and time is not given for you, the best way is to find the change in momentum of that ball. So I need to calculate the change in momentum in this case. See, it is hitting the floor like this vertical wall with an angle theta. I can draw the diagram for you. Let me draw a diagram for you so that it's easy to understand that. A body is striking this vertical wall with a velocity v, making an angle theta here. So this can be resolved into momentum is mv, which can be resolved into components. What are the components? This will be adjacent component because this is adjacent to theta. This is mv cos theta. This is vertical component mv sin theta. I want you to notice the directions carefully. As the momentum is approaching the origin, both the components are approaching the origin, that is before collision. See, what happens after the collision is it is bouncing back with same velocity and same angle as it is given in the problem. So this is also having a momentum mv, which can be again resolved into components. Again, this will become an adjacent component mv cos theta, and this becomes the other component mv sin theta. Again, I want you to notice the directions of the components. As mv is outward, both these components are outward. So if you notice carefully that this mv sin theta of the first component is downward, the second one is also downward. So there is no change in momentum or velocity along y direction. But look at the x directions. It is initially towards the origin. Finally, it is away from the origin. So they are in the opposite direction. So what we can understand is change in momentum is change in momentum only along, of course, x-axis plus change in the momentum along y-axis. But change in the momentum along y-axis is 0 because their magnitudes and directions are same. So change in momentum along x-axis. Change in momentum along x-axis is final momentum along x-axis minus initial momentum along x-axis. Final momentum is mv sin theta minus because you want to calculate the change. Again, I have to put another minus because these two are in the opposite direction. mv cos theta and mv cos theta. So that's nothing but 2mv cos theta. So change in the momentum or impulse is nothing but 2mv cos theta. Substituting our data, 2mv cos, angle is given for you in the problem as 60 degree. 2mv cos 60 sin 30 is half. Both of the 2's can cancel. So that's nothing but mv. So answer for the problem is just mv, right? This is how we have to solve the problem. So the important thing is to know impulse is nothing but change in the momentum and trying to understand how do you resolve vector into components. Most important thing is direction of the components is similar to the direction of the original vector. Same is the second case. This is the second case. Yeah, you can see that. As this vector is outward, both these components are also outward. That's the thing that you need to understand, right? Once you got that, this problem becomes easy. That's it. Thank you for watching.